IP version 4 has been around for quite a while now, and at this rate it looks as though it's actually going to be around for quite a while longer. But what is IP addressing? What's a subnet mask? How do you work out the network ID versus, say, the host ID? And how do computers actually communicate using IP addressing? Well, if that's something you're interested in learning, then stick around and watch this video because that's what we'll be going over. Now this diagram here is a typical sort of network in the sense that we've got various computers, they're all in different networks. They've been separated out by a router here that's got access to both networks, and it's allowing all these computers to talk to one another. Now, protocols used for computer communication, they've been and gone, and what's left is IP. And at the heart of it all is IP addressing. In other words, every device that's in the network has its own specific IP address, and it gives that unique identifier, if you will, because that's what the IP address is meant to be. It's a case of this computer here has got its own IP address, but it knows that if it needs to connect to this specific laptop, then it's going to be connecting to this specific IP, 192.168.1.1. Yes, that's a laptop, but they've got different IP addresses, and that's how the computer can distinguish between these two laptops, for example, because they've both got a different IP address. It doesn't matter that they're in a separate network. Fundamentally, it's a case of each of those, each one has a different IP address, and that's how it knows to identify which computer is which. Now, granted, it's a case of, we're still on IP version 4, and yes, we've actually run out of IP addresses, as it turns out. It doesn't seem to be as big of a push as probably expected to IP version 6, but the principle is the same in that every computer has an IP address, and that's being used as an identifier. So, yeah, protocols have been and gone, and it's a case of IP is what's left. But how on earth did we get to this point of all these IP addresses as identifiers? What do they actually mean, and how do these computers actually communicate through the IP addressing? Now, although IP addressing actually does go on in the background, for the likes of ourselves, well, it's more to do with names. So if you think about it, a computer has a name. We usually assign our computers with a host name, and that allows us to identify them. So for example, this one's called laptop, this one's called tower, this, it's called desktop. This makes sense to us, but it has no meaning whatsoever to computers. It doesn't understand what you mean by tower. So it's a case of, we might have a computer called desktop and we ask it to connect to tower. That does actually go on. There is a system in place to allow you to actually communicate by the names. But when it comes to computers, they don't understand these names. They understand numbers. So, we could take a step where we've got, like, this one's 1, this one's 2, and this one's 3. That still makes a bit of sense to us. But the trouble is, it's decimal. We work in decimal, but computers work in binary. So this, straight away, too, that's a bit of a problem. So we have to start dealing with binary now. Now, that's not too bad. It's, if you're kind of familiar with binary, it's a number that big isn't that big of a problem, I suppose. It's still going to be a bit of a pain if you're going to have to go around and configure computers with binary numbers like this. They are unique in a network like this size, but if you're familiar with binary, you'll look at that number and say, well, this isn't even scalable. And then there's the other challenge, which is, well, what happens when you connect two different networks together? Let's say we've got this network here and this network here. We connect them together through a router. Someone looks after this network. Someone else looks after that network. And, well, for one thing, you're going to run out of these numbers basically pretty quickly. They only go from like 0 to 255 for a start. But the point is, in this particular case, the numbers are the same. There's nothing unique to distinguish these numbers. So if this desktop here, for example, wants to communicate with this laptop, how on earth does it know, the difference between that laptop there and that laptop there? They've got exactly the same identifier, if you will, with the same device from its perspective. So what you actually need is you need a means to actually distinguish between networks. It's not just about distinguishing between the devices, because what happens when this computer wants to talk to this computer? I mean, it's in its own individual network. If this computer wants to talk to this computer, it has to go through the router to get there. So it's a case of we need some means of identifying not just the individual device, but the actual networks that these devices are in. And that's where IP addressing does actually come in. These are the sort of things they did think about, and that's what they've derived is you've got what is basically a network ID and a host ID, but they're combined together. So what you've got is a network ID followed by a host ID. So if we go back to the original diagram here, 192.168.2.1, for example, it's a combination of an actual network ID and a host ID. So what it actually is, it's a 32-bit number. That's what they did back then. I mean, they derived a 32-bit number to represent the network ID and the host ID. And that's, yeah, it's a 32-bit IP address. So IPv6 is a 128-bit IP address. So if you think that looks difficult to understand, yeah, just imagine what 128 bits would be like. I mean, you look at that number, it's just a bunch of ones and zeros. It makes perfect sense to a computer, but it means next to nothing to me. It's way too complicated already. I mean, if I was to like program that into a computer every time I had to assign a manual IP address, or if I wanted to ask a computer what its IP address was, I don't want to be looking at something like that. It's just too complicated. So fortunately, there is a sort of like a presentation layer, if you will. To the computer, it's still a 32-bit number, but for us, it's broken down into a simpler format. So effectively what we do is basically we split this 32-bit number. All these 32 bits, we split them apart into little segments of 8 bits. So we've got 4 segments. Each one's referred to as an octet. There are 8 bits in an octet. So we take the first 8 bits, then the next 8, then the next 8, then the next 8. So we've got 4 blocks of 8 bits. Not surprisingly, 32 in total. So that number there is split up into these little 4 blocks. And then it's converted into something that we do recognize much easier, which is decimal. So that is 192.168.1.1. And that's pretty much what we're looking at on that laptop, 192.168.1.1. But the trouble is, these blocks here are 8 bits. They can vary from anything from 0 to 255. So you can see straight away, I mean, this is 3 digits. This is 1 digit. If we just bunch them all together, how on earth would you distinguish between the octets? So that's where we've got what's called dotted decimal format. So these are decimal numbers, which are split apart, separated, if you will, by a dot. And that's why you'll hear this common pronunciation, for example, of 192.168.1.1. I mean, sometimes you'll just ignore it and just say it's 192.168.1.1. It's relatively easy to distinguish between them, but it's better when you're presenting it in a visual format to have that dot between them. Otherwise, I mean, yeah, if I take those dots out, you might actually struggle. You wouldn't know, is it 19? Is it 68? It starts getting confusing. You just don't know which part's belonging where. So the way it works, though, is if we go back to the original design, if you will, of IP addressing, we had what was called classful networks, and they were very rigid in terms of setting the network ID. So like I say, we've got like a network ID and a host ID. So it's still this one big number, but it's broken up into a network portion and a host portion. So you see this 192.168.1.1, but there's actually 2 parts to it. So in the actual early days, it was pretty easy to distinguish between which was the network and the host, because it was fixed, it was set in stone. So 192.168, for example, anything that started with those 2 numbers, it meant that the first 3 octets were the network ID. So that's it, 192.168.1. That's the network portion of this number here. 192.168.1 represents the network identification. The 1 is specifically the computer itself, the actual host ID. So that was pretty easy to understand, but the problem is, well, it was a case of, even back then, it was soon realized, well, we're going to run out of IP addresses. So what happened was, is they then started making it and well, they gave you the opportunity to get away from this rigid structure, if you will, and be a lot more flexible. They introduced what were called subnet masks, where you could actually break these networks down and you could assign whatever network ID you liked. It didn't have to be those first 3 octets. You could use maybe the first 2, maybe the first 1, whatever. It was very, very flexible, and it was needed because internet service providers were running out of IP addresses. I mean, all the big companies gobbled up masses of IP addresses, and well, yeah, they're not going to hand them back. So it's a case of, yeah, there's not enough IP addresses to go around. So rather than giving somebody a really big network, well, how many IP addresses do you actually need? How many computers do you need to be visible on the internet? Right, okay, then I'll give you this network address, which is smaller, but it's enough to cover, the actual requirements that you have. So that's where this, what was called classless routing comes into play, or routing if you prefer. But before I go there, we're going to need a bit of a crash course on binary. Now, thankfully, you can actually have binary to decimal conversion done in your calculator, and vice versa. But if you're into IT certifications, then chances are you're going to be able to do this yourself. Now, it's also going to feature quite a bit in the actual next section that I'm going to do. So I thought I'll give you a bit of a kind of a brief breakdown on how to do binary to decimal and decimal to binary. So I've got some examples here of 74 and 9, and they've been converted into their binary equivalents. But typically what you'll do is you're working with individual octets. So you've got 8 bits here. And above those, I've got these, what are really just values for the individual bits, if you will. So we start with 1, we double it up to 2, double that one up. So that means that bit there can have a, that represents a 4. If we double it up, we're up to 18, then we've got 16, 32, 64, 128. So if you want to convert, say, a decimal number, so let's say, for example, we've got 74. We want to see that as a binary number. What we do is we'll work from left to right, and we basically just try and we'll turn these bits on depending on, what we can represent that binary number as. By that I mean, say we come to the first number, which is 128. Now, 128 is too big for 74. 74 is less than 128, so we can't turn that bit on, so we leave it set to 0. 64, on the other hand, is less than 74, so it's a case of we can actually turn that bit on. Now, if we go to the next bit, that has a value of possibly 32, but 64 plus 32 would give us 96, so we can't enable that bit, so we set that to 0. It's the same with 16. If we had that bit and that bit, it would have a value of 80. So that's too high. So for that reason, we set that one to 0. So we go to the next column here, which is potentially 8. Now 64 plus 8 is 72. So we're still within our range of 74 here. So we enable that bit. So we set that to 1. We can't use 4 because that would take us too high. But we can use 2, so we've got 64 plus 8 plus 2 is 74. And that's exactly it. That we don't need anything else. So the last bit there we set to 0. And that's all you're doing basically, is you're just going along, starting from the left, working your way right. And you're effectively just subtracting these numbers from that to work out what's left. And then from that you're deriving, which other bits you want. So 74, take away the 64, that leaves us with just 10. That's the only amount we've got left. So yeah, neither of these two line up. So 10, yeah, 10 less 8 is okay. Now we're left with 2, so okay, we assign it to 2. So relatively straightforward there. And 9's much easier. I mean, these numbers are much, much bigger than 9. So it's a case of we've got to wait until we get to 8. So 9 less 8, yep. We can assign that one, we're left with 1, so not surprisingly, we just set that last bit. Now, if you want to do it in reverse, pretty much the same sort of thing, really. It's a case of we've got this binary number here, what is it actually, represent in decimal? Well, you just literally total it up. So 64 is set, 8 is set, 2 is set. So 64 plus 8 plus 2 equals 74. And in this one, well, it's only 8 and 1 is set, so 8 plus 1 is 9. So that's all there is to it. So all you got to remember really is just put your 8 bits down there. So we've got a total of 8 bits. We start with a 1 for the first bit, and we just double them up as we go along. And so effectively we start with 1, and the last bit is a 128. Because 8 bits have a potential value of anywhere from 0 to 255. The reason for that is if we double that up, we'd have 256, so it's pretty easy to calculate. And that's another thing you can figure out quite easily as well, is that in some of the calculations we do, we actually use a certain number of bits, for example. So we might use these first 4 bits, like say like if all of these had a value of 1, we can actually easily calculate the value by looking at the column just in front. So this one here has a possible value of 16. So if you set all 4 of these bits to 1, it's 1 less than that column value is. So those 4 bits, if set to 1, would have a value of 15, which is 1 less 16. If we totaled all of these bits all the way right up to here, so these 7 bits here, if we set these all to 1, that would come to 127. It's 1 less than 128. So I do hope that makes sense. It's not too bad once you get familiar with binary. It's fairly easy to understand, but it's when you start getting into the calculations, yeah, it comes in very handy to be able to understand that binary format. Now these days we use what's called classless routing, or more specifically classless inter-domain routing, also known as CIDR for short. And that gives us flexibility to set the network portion of the IP address how we particularly choose to do it. So we can either have a large network portion, which just means, well, it just means we're going to have fewer computers in each network, but we'll have more networks. Or we can go in the opposite direction where we have a smaller network portion, meaning we've got fewer networks, but we've got more computers in them. So there's a lot of flexibility in deciding what we're going to do, but a common sort of network we could run into is, for example, an IP address of 192.168.1.1, and we have what's called a subnet mask, 255.255.255.0. So that subnet mask is actually used as a means to effectively mask out. It's applied against the IP address to derive the network address, and we've got a lot of flexibility in how we set this up. Now the thing to bear in mind is some operating systems will ask for the IP address and the subnet mask, whereas some will ask for the IP address and the prefix length. These two things mean exactly the same. What they both represent is how many bits in this network IP address represent the actual network portion. So if you look at the prefix length, it's pretty obvious, 24. Once we get a binary, you'll see what I mean. But if we take this IP address, convert it into binary, I've broken it into the 4 octets. So that's the IP address in binary, and that's the subnet mask in binary. So 8 bits all set to 1 is 255. 8 bits all set to 0 is 0. So 255, 255, 255, 0. If you total up the number of bits here, we've got 24 of them, hence the reason the prefix length is 24. So what it means is we've actually reserved 24 bits out of this IP address to use for the network, and what's left is going to be used for IP, well, specifically for the IP portion, if you will, that goes to the individual computers in this network. So we've reserved 24 and we're left with 8 for the computers. So what we do to derive the actual network is we perform a logical AND against these numbers. So when it comes to this binary and ANDing 2 numbers together, 1 and 1 means 1, anything else means 0. So 0 and 1 means 0, 0 and 0 means 0, 1 and 0 means 0. So this is the actual result of doing an AND against these two 32-bit numbers, which in decimal is actually 192.168.1.0, and in dotted decimal format it's 192.168.1.0. So once you get more familiar with this process, you can basically see that what we've done is we've reserved the first three octets, so 192.168.1, effectively to represent the network, and then we're left with the fourth octet to assign out, IPs effectively to the actual individual devices or computers in the network. So because we've got 8 bits, we've got a range of anything from 0 to 255 that number can represent. These 3 octets are fixed. This is the network. We can't change that, but we can set this from anything from 0 to 255 when we're assigning an IP address to a computer. The only thing to bear in mind is, well, the first number that's in the range can't be used. That first number represents the network address itself. Now, I have come across systems that do allow you to use that and assign that to a computer, but it's something that most vendors probably wouldn't do, and it's not really common anyway, so I would forget about that and just ignore basically the first number. We also can't use the last number because it represents what's called a broadcast address. So basically, although we've got a range of 0 to 255 that this fourth octet here can be used to assign out to computers, we've got a potential 256 numbers available, but we're reserving 2 of them, the first and the last, meaning we've only got 254 numbers left. So that means we can have up to 254 computers on this network. So the first computer would start with an IP address of 1, and the last one 254. So we're quite flexible here. We don't have to necessarily use them all in sequential order. Use them, hand them out as you please. I mean, one common strategy is 254 in this case is left to be used for the actual router here. Some will use the first one instead. It really varies. It's entirely up to you. There's no hard and fast rule. It doesn't really matter. You could use any number as long as you're consistent, I suppose, as long as you know which is which. And as long as each of these computers all have their own unique IP address, it doesn't really matter what you use for your default gateway. So we've got quite a bit of flexibility, quite a big range here of potentially 254 numbers. Now, there's a few things I will point out is when you get into especially like the routing, we have what's called a network prefix. And this is a way of representing the network. We have a network address, which is 192.168.1.0. We then have a / followed by the prefix length. So you can either derive the prefix length from the subnet mask like that, total up the ones, however you do it, it's entirely up to you, but it's a case of there's different ways of representing the network. You'll either see it as maybe 192.168.1.0 with a subnet mask of that, or maybe you'll see a network prefix. As long as you know what these all represent, it's pretty straightforward. And just remember that you can't use the first number and you can't use the last number because they're reserved. Now, one thing I'll point out when it comes to this subnet mask, because as I was saying, you can be very flexible. You can basically reserve more bits if you want. So if you want more networks, you'll start borrowing or reserving more IP addresses. So you'll start borrowing that bit there, then that bit there, then that bit there. And that's the one thing to point out is you start on the left and you work your way to the right. One thing I can't do is I can't have these 24 bits here and I can't reserve that bit there as well. If I want to reserve more bits to represent the network, in other words, I want a bigger a number of networks, I've got to reserve that bit. If I want more, I've got to reserve that bit, then that bit, then that bit, and so on. If on the other hand I want to have more computers in these networks, I'll start to reserve fewer bits. So in which case we'll drop from say 24 bits to 23 bits, or 22 bits, or 21 bits. So the smaller the prefix length, effectively, the smaller that network range is, we'll have more and more computers in each individual network. On the other hand, the more bits I borrow, the bigger the prefix range or length gets, and then the fewer computers I'm going to have in that network. Having fewer computers in the network but more actual networks makes a lot of sense for an internet service provider, because it'll be a case of they'll be allocated a certain IP range, if you will, a certain block of IP addresses, and they need to chop those up into smaller little networks for their customers. So that's one of the main driving factors behind CIDR. But what does this actually all mean? I mean, it's all very well knowing a network address, which part represents the actual network, which part represents the actual computer. What does it actually all mean? I mean, how do these computers actually communicate with all this? So to explain how this IP addressing works and how computers use it to communicate, we'll use this network diagram here. So relatively straightforward in that we've got two networks. This is the 192.168.1 network, whereas this is the 192.168.2 network. And we're using a router here to join the two together. So all of these computers will have a specific IP address, then they'll have a subnet mask or a prefix length, and they'll also have a default gateway. So for these, it's 192.168.1.254, for instance. So with that information, a computer can decide when they want to talk to another computer, if that computer is either in the same network as itself, or if it's in a different network. If it's in the same network, it can talk to it directly. If it's in a different network, it needs some sort of intermediary device to get that traffic there. And in this case, that's where this default gateway idea comes in. So if this laptop wants to talk to this PC here, it's a case of it's going to have a look at this IP address. It's going to find out that to communicate with that computer, it needs to talk to 192.168.1.3. Now, if we go back to our calculations here, well, 192.168.1.0 is the actual network address here. So we know that those 3 octets there belong to the network portion, and that 4th octet is reserved basically for the actual IP addressing for the actual computers themselves. So this computer will be able to tell that this computer here, because of that IP address, is in the local network. Now, on the other hand, if this computer wants to talk to this PC, it'll see, well, the destination is 192.168.2.2. It's going to work out straight away, well, 192.168.2 is a different network to 192.168.1. So while this laptop here can communicate directly with this PC, for this laptop to reach this PC, it needs some sort of intermediary device, hence the reason for the default gateway. So let's say these two computers do want to communicate. Because they're in the local network, the same network, what's going to happen is this computer is going to get its information. It's going to stick a label on to that information that says the destination is 192.168.1.3, and it's going to put on a source of 192.168.1.1. So that way this computer, when it receives the information, it knows who to send the reply back to. So it'll send the information. I mean, I won't explain the mechanics of how that works because that's different. All of this stuff that's going on here when it comes to IP addressing is layer 3, but effectively these computers will talk at layer 2 as well, and then we're down to layer 1, but we're only interested in layer 3 really, which is the IP addressing. So the information goes over to this PC here. Now when it needs to send a reply back, it's got the source address, so it knows it needs to send a response to 192.168.1.1. It's going to come to the same conclusion that this laptop is in the same network, so it'll send the response back directly. Now, as I've explained, that computer here is in a different network to the laptop. The process is just slightly different though, in that the laptop is actually going to take its information. It's still going to send it to the destination IP, which is 192.168.2.2 in this case. Still going to put in a source address of 192.168.1.1. It doesn't know effectively what this network consists of. It doesn't know things like the subnet masks, prefix links. It knows nothing about it. But this default gateway is a kind of last resort or all or nothing approach, where if there's a computer that the laptop needs to reach and it's not local, it just forwards that request on to the router and it leaves it to the router to then get the traffic there. And that's exactly what the laptop does. It just forwards the traffic to the router. So when that reaches the router, again, I'm not going to go into the mechanics on layer 2 or 1, but once it reaches the router doesn't change anything in terms of the IP addressing. It just does its own checks and says, well, this is destined to go to 192.168.2.2. It has a look at its own routing table and sees, oh, well, I've got an interface in that same network. I mean, I've got an IP ending in .254, yours ends in 2, it's in the same network, and it just sends it directly to that PC because they're in the same network and they can communicate. So in terms of the IP addressings, nothing's really changed. The process is the same. The computer's just taking its information, wrapping it up into something that the network can understand with a destination IP and a source IP, except in this case, it's forwarding it onto the router to then handle. So it's kind of similar to us where we might have a letter to send to somebody. We don't know how to get it there, so we put it in an envelope, put on the address, put it in the mailbox, and that's it. We just assume and hope that the actual postal service will be able to get the actual letter there. And this is pretty much the same. It's an all or nothing or last resort is the default gateway. But in this particular case, yeah, the laptop sent it to the router sent it to the PC. Now the PC is going to come to pretty much the same conclusion as the laptop when it wants to send its reply. The laptop's in a different network, your 192.168.1 and part of the 192.168.2 network, and so in which case it's going to send the response back to this router. So the destination will be 192.168.1.1, the source will be 192.168.2.2. So when the router gets that information, it'll have a look at its routing tables and it'll say, well, actually this IP address here, I can reach that through my own network card interface here, and I can reach it directly, so it'll just send the actual response back direct to the laptop. So it's just acting as an intermediary between these two computers. So as far as the work done by the laptop, nothing's really changed, except instead of going direct, from this laptop to this PC, we're having to take a bit of an intermediary path to get from this laptop to this PC and vice versa. So it's relatively straightforward to understand how that part works. As I say, there is a lot more to it because we've got other layers to think about, but we're really considering the actual IP addressing here and how the actual IP addressing gets assigned, how we derive things like the network IP addressing, the host portion, the network portion, and so on. And the computers go through pretty much the same process. Now, there is one IP address I haven't mentioned here, which is this one here, this broadcast address. I mean, as I say, the network address doesn't get used, but the broadcast address does. It's a reserved IP address, but it does actually get used. So when this computer knows it wants to talk to this computer, it knows to send the traffic to 192.168.1.3. But there's a lot of things go on within a network where computers, they either don't necessarily know the IP address of who it is they need to talk to, or it might be a case there's some service where a computer needs to talk to everybody on the network, or there might be some redundancy technology that needs to tell everything about on the network about it. There's all sorts of reasons why we have this thing called a broadcast address. And it literally is like the equivalent of a tannoy. I mean, this is like, two people having a conversation over a telephone, for example. They've got direct communication. When it comes to the broadcast, that would be the equivalent of somebody, getting onto a tannoy and telling everybody in their shop about something. Because that's what it's for. It's not an IP address that belongs to any individual computer. It's an IP address that every computer will listen to. So if this laptop, for example, were to send traffic out to 192.168.1.255, which is the broadcast address, it will be sent to every single device in this 192.168.1 network. It's then up to the actual computers to decide if it's of any relevance to them and whether they should respond to that computer or not. But that's it, basically. It's just a slightly special IP address that's used to talk to every device, whereas each individual computer's got its own specific IP address to allow these computers to talk directly to each other, whereas the broadcasters to talk to everybody. So that's the only difference, something to bear in mind as well. And unfortunately, some operating systems do tend to be quite chatty and they do actually talk to everything. And that's why a subnet mask like that's a bit more popular, because the more computers that are actually in the network, the more chattier things become. And the problem is, any traffic that reaches a computer, the computer actually has to stop. It has to investigate that information to see whether it's relevant or not. And if it's not, it has to throw it away. So if there's too many computers, it can get to a point where it's just too noisy. In which case, yeah, it becomes less and less practical. So there's a bit of a trade-off between how many computers you can have in a network. But hopefully I've explained enough about how we got to this whole idea of IP addressing, how you derive things like a network address and so on, and how these computers actually use IP addressing to communicate with each other. If not, please drop a comment in the comment section below. Do ask questions and I'll do my best to answer them. Well, thanks for making it to the end of this video. I really do hope you found it useful. If so, then do click the like button and share, because that encourages YouTube's algorithm to suggest it to other people who might find it useful as well. If you're new to the channel and you'd like to see more content like this, then yeah, do subscribe. Just remember to click the little bell icon though, that way you'll get notifications when I send new content out. If you've got any comments, any suggestions, if you want to leave any feedback at all, please post that in the comments section below. And if you'd like to support the channel, I've left links to both Patreon and PayPal in the description below. But above all, thanks very much for watching. I'll see you in the next video.